also have career development, such as CNN job databases, free career consulting. So here are the dates for the upcoming career consulting sessions and career pathway workshops. Also, you have the conferences and events, such as national meetings, such as the ACS Fall Meeting, which will be in August 21 through 21st in Chicago, Illinois. The regional meetings, such as the Southeastern Regional Meeting for the ACS, which will be in San Juan, Puerto Rico from October 19 to 22. And also you have inclusive groups and committees, such as the Women Chemist Committee, Senior Chemist Committee, the Committee on Minority Affairs, Chem Clubs, and YCC. So what is YCC? Well, the Younger Chemist Committee is a group for younger chemists and early career chemists with a vision of transforming the world through chemistry. And the mission is to advocate for, develop, and support rising chemists to positively impact their careers, the ACS, and the future of chemistry. So the Eastern US YCC partnership has a lot of local sections, including Northern New York, Connecticut, Eastern New York, Philly, Rochester, Puerto Rico, St. Louis, Virginia, Indiana, and North Carolina, and also international groups such as Brazil. So we do a lot of events that have to do with career development, self-care, and a lot of directed workshops in different areas of chemistry. So we also want to give a shout out for in 2021, we had the best activity or program stimulating the member involvement, which is the Day in the Life series, which is the one we are carrying out today also, and the Outstanding Local Section Younger Chemist Committee Award. So what can you do to get involved with YCC? You can attend YCC events at national meetings. You can join or start your own local section and apply for YCC sponsored awards. So now I'll introduce our speaker, Dr. Dalice Piñero Cruz, which is an assistant professor of chemistry at the University of Puerto Rico, Piedras campus. She made her bachelor's degree in natural sciences and her PhD in chemistry from the University of Puerto Rico at the Rio Piedras campus. After earning her PhD, she worked as an invited researcher at the University of Notre Dame in Indiana and the Institute of Material Science in Greece. She also had a postdoctoral experience at the Institute de Kim Lamatir Condensate. I'm hoping I said that correctly. And currently she is an assistant professor at the UPR Rio Piedras and the director of UPR's Molecular Sciences Research Center Single Crystal X-ray diffraction facilities. And her lab, her research focuses on coordination chemistry for biomedical, catalytical, and sensing applications. So without further ado, I give the floor to Dr. Piñero, and we gladly welcome you to this event.
Thank you so much, Alejandro, for this kind introduction. I am really excited and delighted to be here. I hope that within this little time that I will be presenting to you what we are doing, that you get excited enough to go and grow crystals, because that's what I would like you to do, to grow crystals and to feel excited about knowing the structure within those crystals. So I'm going to start sharing my presentation. I know that this is quite formal, and that we will all will have later on a Q&A. But if there is something that is really, really stressing you and you need to ask a question, please feel free to do so. I hope to do with this presentation honor to my fantastic students that have invited me here. I'm really a bit nervous because I know they are cheering for me, and I don't want to let them down. So I hope that by the end of the day, I made justice to the invitation that you have made me, and I'm really grateful for it. So this is the day, the title of this series is A Day in the Life of a Crystallographer. which I wish that all my days would be the day of a crystallographer. But I'm also a synthetic chemist, and I'm very happy to be a synthetic chemist, which means that prior to go to the lab, we do synthesis first. But let's talk a little bit more on the direction of just crystallography. I'm not going to direct anything of this to the fantastic materials that we're aiming to do in my lab. So just the crystallographic part. Let's see, for today, I'm going to start with explaining a little bit about my trajectory, what brought me into crystallography, what I do on a normal crystallographic day. I'm going to talk like one slide on the history of crystallography, and that will not do honor to the extensive research on the development of the technique. This is yet another full day topic, but I encourage you to participate to any crystallography course or summer school that you can, and you will get a full spectrum of how the technique was developed, and that would be something that is super interesting in itself. Then I'm going to talk to you a little bit about crystallography 101, what the surface of it, because again, this you can do a full PhD and extend it to your life commitment into studying crystallography, and this is what we do. Then I'm going to introduce just very quickly crystal growth techniques. And finally, we're going to look at the cool and current crystallography projects that we are doing, not only my students, but students of other PIs at the University of Puerto Rico. And I'm going to give one conclusion and the acknowledgements. So let's start with my trajectory. I'm going to pass this very fast for the interest of time, but then again, we can discuss this later on. So I put here what is started with one crystal structure. So in my before finishing my PhD, when I was doing my bachelor degree, I would say on my third year of my bachelor degree, I was lucky enough to start working with iron pyrrosolates. And from then, we started working on substituent on the pyrosols that will give a very particular crystal structure. That is this one that I have to the right. And this crystal structure was what started everything for me. Because then we were a synthetic chemist, you always start think about how to produce or how to use, let's say if you're an inorganic chemist like myself, use metals, use ligands, and look at the products that you form. But in this case, growing a crystal is like your ultimate goal, because you know that you can characterize it fully. And at that time, we discovered that there was with iron, we could have a very similar structure with pyrrosolates as you would have with carboxylates. And for me, that was a really huge discovery. And the night that we, with the postdoc, we solved the crystal structure and we got the material, I couldn't sleep. I was so terribly excited by the fact that we have created a new material and that we knew what all the atoms in that crystal, the location, how they interacted with each other, everything, all the information. That led me into thinking that I definitely wanted to be a chemistry major and to do a PhD in chemistry, because originally I wanted to be a doctor in medicine. So that and some other experiences opened the field of chemistry for me, and the deep knowledge that I was in a path of research. So in that case, I got that crystal structure, graduated and decided that I still wanted to do crystallography. continued with back then, my mentor, Dr. Rafael Raptis. And then after my PhD, I went to the Institut de Chimie de la Matière Condensée de Bordeaux because I wanted to study magnetism. And I went to also to another institute as a postdoc after that postdoc with the Institut de Sciences Chimiques de Rennes, because I also wanted to learn more about electrochemistry. And then I returned back to Bordeaux and work at the Université Bordeaux and the Centre de Recherche Paul Pascal, also to again retake on magnetism. And it's always, when you think about it, in my life, it was always wanting to add a little bit more of understanding to the properties of the crystal structures that I was obtaining with my synthesis. So it has been like a constant in my life, that search of properties and structure. So just to make this very short, this is the actual path that I have done as a grad student. Again, I went to Notre Dame, as Alejandro was saying, to do a little bit of radiation tests. Again, looking for properties of my crystal structure, especially on my iron pyrastolate work. Then as a postdoc, I went to Greece and France to do more studies on that related to electrochemistry and magnetism, again, to bring properties into structure. And then I returned to the University of Puerto Rico, wanting to establish a group that would do absolutely that would do synthesis, grow crystals, look at their structure, and then from there, develop knowledge into why they have the properties that they have. So this is a little bit of a view of Puerto Rico. I cannot do a seminar without showing this slide, because my message is also that you should always visit different places, and Puerto Rico is a very nice place to visit. Here we have the University of Puerto Rico. We have the interior, which is very mountainy and it's beautiful. We have all the beaches that are fantastic. We're super big on music, food, and if you like old buildings, you can come to Old San Juan and have a lot of fun. But anyway, visit the island. But when you come to Puerto Rico, just think that there is a crystallographic community here also waiting for you. So as a crystallographer, what do I do on my regular normal day? Well, I don't have to do other tasks. I give maintenance to the X-ray diffraction instrument. Sorry, there is a typo there, but I give maintenance to the instrument, and that is part of my responsibility as a director of facilities. I receive new projects from different groups. I prepare training activities for students, undergraduate and graduate, scientific staff, postdoc, everybody that is part of our scientific community. I offer classes and workshops on X-ray diffraction analysis. I think that that is the only way I can get people to really learn X-ray crystallography. We have to be continuing educating people, not only classes for students, but also for people in the industry. And I have delivered many of those. More than 200 students, again, have been trained. These are students that have not taken the courses. These are students that have been trained directly at the facilities. Also, one of my favorite tasks is to help students with their crystal structures. And actually, we have a pilot group of students that are currently working on their papers. And my idea is that we can continue creating crystallographic groups to solve problems and to everybody kind of help each other into publishing their crystallographic data. And obviously there is the part of writing manuscript on crystallographic data. And something that is very important for crystallography and for X-ray diffraction is to participate in NSF panels to support new crystallographic facilities. And this is important because what we are really seeing now is that this technique is so mature that in a lot of different institutions, you have different crystallographic centers, both for big institutions and for small institutions. And I think that crystallography should be should be available. It should be there in the preparation of undergraduate and graduate students. So if more people could go and be in front of an X-ray diffraction instrument, they will, and to collect their own data, they will really be excited about the chemistry that they're doing. And that's why I think that funding more crystallographic facilities is the key to getting students involved in higher education. So this is the facility. Here you can see my student and co-host Keisha. Here is our instrument, our single crystal instrument. And here we have two microscopes. There is another one here that where we students go and they mount their crystals. So again, I don't like the feeling of being the person responsible for all the crystallographic work in an institution. I like students to get involved. I like students to do their own work and to select their own crystals, mount them, collect their data, and solve their crystal structure. That is my aim. So like this one, there are so many images of my students and other students from other PIs doing their own crystallographic work. So I'm very happy about that. So this is what we have. Let me see if I can put my pointer. So this is basically what the instruments that we have at the Molecular Science Research Center, which is part of the University of Puerto Rico, but it's outside the campus of Piedras. And what we offer is training for people that are conducting research. We offer services to the industry, or we try to, and we try also to train as many students, as I said, and faculty as we can. We were funded by an NSF MRI grant, which is how we acquired this very nice Rigaco instrument. And we have the aim of being open for everybody that needs crystallography, crystallographic services, not only in Puerto Rico, also in US mainland. So if you have any other, any need for crystallographic services, you can send me an email and or which is here, or send an email here, and we will be very glad to provide a reply or quote. Here are some of the activities that the student undertake. These are the workshops that I develop. I routinely give 4 workshops during the semester and it is free for students, so anybody can enroll. And also we do offer services, paid services, through the Material Characterization Center, and they run all the management of our quotes and the hours, but it's not expensive at all. So I could directly direct you, if you need from our service, to the Material Characterization Center director, which is Dr. Edgar Resto. Now, that's where we were, and that's what I do on a regular basis: solve crystal structures, train students, manage the facilities, work in collaboration with the Material Characterization Center. But so now let's go into the part of the talk of where we talk about a little bit of the history of X-ray diffraction. Now, again, as I was mentioning, I do not intend to put everything in a single slide. There is so much missing information here, and I really encourage you to look on the development of the technique. It's really rich and interesting. It's extremely interesting from a historic point of view, but everything was born with the discoveries of this new rays, or this new particles, as it was called at the time. And this was done by Willem Conrad Röntgen, And he discovered by the 1895, he discovered the X-rays. And with this, I don't have the images of what was the first X-ray image, but you can find it on the web, which was the hand of his wife. And from then on, a lot of advancements were made on this regard, for both not only in chemistry and biology, but in medicine, in criminology, in all the fields with these discoveries of X-rays. How the X-rays were later on developed is due to the is thanks to the intervention of other people from the crystallography community. And with that, we have the Braggs, Lawrence Bragg and Henry Bragg, that in 1913 developed the what we will see later on, which is the Bragg's law, and the definition of how waves interact with planes in a crystal. And through that, we can determine the interplanar distances that gives us the idea of what are the spacing between elements in a crystal structure. We also have Max van Laue, that by 1914, he discovered that crystals diffracted X-rays. And that also contributed to the development of the technique. And also we have the development of the theory of the Ewald sphere by Paul Peter Ewald in 1913, which gives the description of the crystal model through the Ewald sphere, both in using giving laying the theory for real and reciprocal space. And this was very important because this is how the analysis can actually be performed. But those are people that help develop the X-ray diffraction technique. But I want to mention two women that are terribly important in this development, which is Marie Curie, because obviously, and she's the heroine of a lot of us, because without her discovery of this radium and polonium elements, many techniques concerning radiation or ionizing radiation would not be able to develop. So I think she's one of the pioneers of the technique, even though she was not directly involved in the X-ray diffraction technique. She's very much important for the technique to be developed. And then Rosalind Franklin, because without her, James Wanson's and Wanson's Crick wouldn't have determined the double helix crystal structure of DNA. And I think that this is one of, if not the most important crystal structure that has been determined. So having this contribution from them had helped grow the X-ray, the crystallographic field as a whole. Now let's go very quickly into crystallography 101. So the first thing is that we will be talking about crystal lattices. I mean, periodicity and symmetry. And this is always, I do this movement, periodicity and symmetry, and the students laugh, but it is actually what the two conditions that we need for a crystal. And we are going to give some definitions, and we're going to see what is not a crystal and what it is a crystal. We're going to be discussing a little bit about the unicell, the 7 crystal system, and I'm just going to mention the possibility of having other categories like the 14 Bravais lattice, which is again not fair because there is so much to know about crystallography that I will not be able to talk today. But then again, if you are excited about this, please take a course in crystallography anywhere. And I believe me, you will be very much into crystallography. So what are crystals? And this, I wish this could be very interactive, in which I could hear my audience saying what they think are crystals. But let's start by some of the answers that are either on the web or that some people have said in different seminars. So a small piece of substance that has many sides and that is formed with, when the substance turns into a solid. The other one is a clear hard mineral that is either colorless or very light in color that is used in making jewelry. And other things that I have seen is a special type of glass that is very clear. So these are not correct answers for what are crystals. Okay, these are very vague and not necessarily true of what crystals are. So let's first think that crystals need to have an internal structure that is enclosed symmetrically and arranged in planes in the surface. So here we can see the very clear example of what amorphous solid. So what I always say, like this table, this desk, you see, we are seeing examples of what mine is a wooden desk. So this is it's a solid, but it's not organized. So this is not obviously a crystal. For it to be crystal, the solid needs to be, first of all, homogeneous. It needs to be repetitive in the 3 dimensions, all 3 dimensions, in patterns of atoms, ions, or molecules with fixed distance between constituent parts. Also, you can say more specifically that a material is a crystal if it has a sharp diffraction pattern. So I always tell my students that sometimes you may think that you have crystallized something, but you have grown a glass. And the only way to know if you have a crystal or not is not by looking at it, it's by actually looking at its diffraction pattern and to see if it complies with Bragg's law. So what is, now that we know what is a crystal, let's see what is crystallography. So it's the study of atomic and molecular structure. Before it was thought that it was the study of crystals only, but now we have extended the International Union of Crystallography have extended this definition and devoted it to the branch of science devoted to the study of molecular and crystalline structure and properties for far-reaching applications in many fields. So normally now we don't just look at structure, we do the structure properties relationship. And crystals can be composed of different type of atoms, molecules through different intermolecular forces. You have crystals coming from ionic forces. You have metallic crystals. You have crystals growing from covalent networks, and you have crystals that are purely molecular in nature. So after you have grown or you have faced yourself with a crystal, you need to solve the crystal structure in order to know how the atoms are related to each other. And this is what is called to solve a crystal structure. So it's not that it's a given, you need to do the work. And what is to solve a crystal structure is to determine the precise spatial arrangements of an atom in a chemical compound in a crystalline state. So actually and this is something that I often tell my students, when you look at the crystal, think about how atoms are arranged, their direction towards each other, their spatial connectivity. Everything will be defined through the analysis. And with this, what is the information that can be withdrawn? Again, connectivity, conformation, accurate bond lengths and angles, stoichiometry, the density, symmetry, and in 3D packing of atoms in the crystal. So actually is knowing the interior, the full extent. It's like taking and making a test to your body and knowing the exact composition of it. So this is what is to solve a crystal structure. Now, something that a lot of students ask, and something that is very important for you to ask yourself, is why do we use X-rays? In fact, nowadays we have many other sources, but let's just focus on X-rays for now on. So the first thing that is important to know is that there is one simple reason why we need X-rays for this experiment. We don't use UV, we don't use microwave, we don't use radio wave, because we need a wave that would be matching the interatomic distances that atoms have in the crystal lattice. And that distance is related to the distance of the X-rays. That's why you use that energy source. Otherwise, we would be using any other, the part of the electromagnetic spectrum that matched that distance. Now, what is an X-ray diffraction analysis? It's to take and process the radiation of the X-rays that, keeping their wave number, is converted by interference to the lattice of the large number of observable reflections with characteristic directions in space. So we are going to see this interference of the lattice into a large number of observable reflections. And this is what we can see if we would look at an image of what happens when a beam hits a crystal and is projected to a surface. This is what we would be observing. And if you can see here, this
Sorry, Dr. Piñero, you put yourself on mute.
Okay, sorry about that. The laser pointer was a bit interactive. So these reflections that we see here, if you can see, they are at a particular distance from each other, at a particular position. And if we take that position, we can make a relationship between the interplanar distances through Bragg's law. Also, we have intensities, and with these intensities, we can have an idea of what are the atoms that participate for that particular family of planes. So again, what we are going to be measuring is the direction of the reflections and the intensities. And this will give us, again, an idea about the atoms and the unit that repeats itself in the crystal and the atoms that form that unit. So now I said that atoms are and molecules in a crystal are homogeneous and are repeating, and they have some symmetry and periodicity, which are very important characteristics. Now, because there is the aspect of symmetry and periodicity, we then can think that crystals are composed of units or boxes of volume that are extended in all three directions. And those boxes can be described in terms of what are called their three direct vectors and the angles that are between those vectors. So these are what are considered the building blocks of your crystals. And those basic vectors can be described by three letters that we normally use in crystallography. And these are most common parameters, A, B, and C. And the angles that are between those are alpha, beta, gamma. And again, I'm just going to mention this like very, very quickly. But if you consider this as empty spaces, and this is how you actually should consider it, you should not consider that the vertices describe particular atoms, because they don't. So these are lattice points. And those spaces may contain one atom, one molecule, a few of them, or a huge domain, like for instance, like a protein. So, but what it is consistent is that it repeats in all three directions. Now, in crystallography, you have two separate categories. You have the people that do small molecules, and you have the people that do macromolecules. And those are the people that do normally like work with proteins and DNA crystal structures. Normally, how you can see if you have one or the other is by the length of your basic vectors, which in the case of small molecules, traditionally or normally is from 3 to 40 angstroms of small. And if you have something that is much larger than that, it can be described or put into the realm of macromolecules. And so one of the things that I always tell students is when you are trying to send crystals of your proteins to a synchrotron source, check in our instrument what are the parameters of your unit cell, that because you don't want to be sending cells to a synchrotron source. So that's one of the ways of doing a very facile assessment of what you have in your crystals. Now, I'm just going to mention this, but very, very quickly again. There are 7 crystal structures, and this depends. Remember that we were saying that we are going to identify the basic unit, the basic repetitive unit, and this is the unit cell. And that unit cell that is composed of 3 main vectors can have a different orientation of those vectors and different dimensions. Depending on the dimensions and orientations, thus the angles, you will have 7 different categories. So we can go from the most symmetric, which is the cubic one, in which all basic vectors are equal and the angles are orthogonal. And we can go then to put one more restraint, or to have one more degree of freedom when the tetragonal, for instance, one of the sides is no longer equal. In the orthorhombic, all 3 sizes are different, but again, we keep the orthogonality of all the angles. Then we can, we also have unit cells that could be hexagonal, meaning that one of the sides could be 120 degrees, but you have a C6 plane. You can also have a trigonal one, which is having that rhombohedral cell within that hexagonal face, where all angles are different than 90, but the same within them. And you can have a monoclinic system, which is again the more lower in symmetry, in which you have just 2 sides that are equal, but under the monoclinic system, you may not have, you may have all sides that are different, but then you keep the alpha equals to gamma at 90 degrees. So it means that you keep one angle different and 2 angles the same. And then you have the triclinic system, in which you have no symmetry related. All angles are different, all sides are different. So within that knowledge, you can state what is the system type of crystal that you have. Now, choosing the unit cell to know which crystal system you have.
Excuse me, Dr.
Yes.
Piñero, we're still on slide 16. I don't know if the presentation has changed.
Yes, I am already in a very different slide, in slide 20. Let me see. Give me 1 second. I will stop sharing and I will have to come back, okay?
Okay.
Okay. Can you see me now, slide 20? Or is still in Is it now in slide 20?
At least I see a black screen.
I'm trying to change my pointer options so that I can work with the, okay, now. Can you see my presentation now? Then on slide 20?
It's still a black screen.
Oh, wow. Let me see something. Can you see my presentation now?
We still can see it. If you want, you can send it to Keisha and maybe she can present it for you. At least the screen sharing.
1 second. You cannot see anything.
No, it's just a black screen.
That's very weird. Okay. I'll send the presentation. Let me try it one more time. Can you see my presentation?
Not yet.
Wow, and it has the green banner and everything. Okay, then I'll send it to you so that it can be fully finished.
So we can start with the Q&A until we get the presentation again. So the first question from Gabriel Espinosa. I have a few questions, Dr. Piñero, as a newbie to crystallography. One of them is, since I have perceived that this field of chemistry is not very well known and is sometimes seen as heavily mathematical or theoretical, where will you suggest one could begin studying crystallography?
Well, I would suggest to start studying crystallography at the undergraduate level. I don't know if that would be the case, but actually it doesn't matter which level you are. There are crystallography summer schools by the American Crystallography Association, the ACA. In Europe, there is a lot of summer schools from the International Crystallography Association, Union of Crystallography. And they also provide a lot of summer camps. The summer camps are for undergraduate students, graduate students, postdoctoral researchers, people from the industry, academia. It doesn't matter the level. You can always join the American Crystallography Association or any in Europe. But if there is a crystallography facility near you, I'm sure there is a training, for instance, in Puerto Rico, and this is one option that I will offer. Again, I give training in crystallography all semesters. So one way is to enroll yourself in those training sessions, and I give always introduction to crystallography. And if you're really interested, you can send me an email and I can send you the dates in which we are planning to do this. So that's that for me, that would be the best way to know about this technique.
Dr. Piñero, did you send the presentation to?
Yes, I have sent it to you. Check if yeah. I'm sorry about this. I really don't know why it wasn't showing.
I haven't received yet, but if you could send to Alejandro. Oh yeah, no, sorry. Yes, I received. So we can pass to the second question until I open the presentation. So the next question is, do you think graduate level training for your field is absolute necessary to whom already in industry and one have career turn?
I missed that last part, Keisha.
All right. So do you think graduate level training for your field is absolute necessary to whom already in industry and want have a career turn?
Okay, so is graduate studies needed for a job in the industry? It depends on what level you want to reach. If you want, again, with a bachelor in chemistry, you're well trained to do whatever technical work is needed in the industry. However, if you want to pursue a higher position, yes, graduate studies will be needed, or you can stay longer and achieve those if with more time in a particular place. I will always think that if you have that question, you should definitely go for aim to grad school, because it means that you have something inside of you that is telling you that that you can go to grad school, and yeah, you should find out.
All right. The next question, which is in the chat, can X-ray diffraction techniques be used to detect defects in the crystal structure of materials and even detect where it is?
No, I would say that it is what we get. Okay, so to one part yes, and to the other part no. So can it be used to see about defects in the crystal structure? Definitely yes. Everything, if you have different type of defects, will somehow showed in the either on the lattice parameters or on the structure factors, meaning that it will influence the intensities at some point. But what we do get is the percentage of the unit cells that have the scattering. And so to localize a defect within that crystal structure, again, since what we get is the total value of the scattering, is something that you cannot do with the X-ray diffraction technique per se. For that, you need other surface analysis to look into that, and other to use microscopy techniques for it.
So we have another question. How could I find a single crystal structure in a library?
Okay, so you can use different libraries depending on the crystal structure that you're looking. you can go to the, if you're looking for a crystal structure of a protein, you can go to the protein data bank, and that's the library for those type of crystal structures. The Cambridge Structural Database that I wanted to talk at the end has over 1. I think it's 1.5 million crystal structures. So everything that has been crystallized with a carbon atom inside can be found in the Cambridge Structural Database. There is a database for inorganic materials, and if it's just inorganic, you should go to that database. So I think that those are the 3 complete databases that exist in terms of crystallographic information. So definitely, yes, all of them, and no, I think the protein data bank, no, but the Cambridge Structural Database and the inorganic material database require license.
All right, we in a few seconds.
I think that it's Keisha, for the interest of time, I wanted not to forget showing the work of the students. So let's go past that point, because I don't want to. I can see that already we have I have extended a little bit. So let's go to the cool projects that we that some of the students here at the University of Puerto Rico are doing. And this is, again, thanks to Alejandro that has said it at the beginning, with the course on crystallography that students have done, and the training that they have received at the X-ray diffraction facility, they are now into doing their own crystallographic work and growing their crystals from the materials, especially in labs where there was no crystallography going on. So I'm quite happy about that. So let's see the first project. The first cool project is, I wanted to highlight the work of Alejandro Burgos. These are his beautiful crystals with his ferrosinil chalcones, and these crystals grow in different ways: solvent evaporation, vapor diffusion, and he can one day, I hope, talk about his own crystal structures, which are in the next slide. And again, he uses crystallography to help, first of all, understand the structure and the intermolecular interactions that are within his crystal structures. And he can see whether the ferrocene is more eclipsed or staggered, depending the substituent that they have. He studies system 1 and system 3 of these chalcones with different substituent in the benzene ring. And again, he sees, and you can see it downstairs, a very marked differences in the crystal lattice that he gets. Then also we have the work, let's go for the next slide, please, of Alondra, that is from another research lab, but she used to be working with also ferrosinil furanes chalcones, and again also so very marked differences between and also polymorphic structures within her furan chalcones. And we're in the middle of writing a publication about them. So this is very interesting crystallographic work. Now let's see, other presentation is by one of my students, which is Victoria Soto. She is growing crystals using, in this case, solvent diffusion. And both Victoria Soto and Keisha work with different dithiolane derivatives. And here we can see one of these benzyl ketone dithiolanes. And this is a very interesting work from her side. There is some polychromism and these crystal structures, but I'm not going to be discussing about that now. Then let's go to the other crystal structures from one of my students, which is Keisha, here with me, and we are looking at a lot of dithiolane the possibilities, and within them, many of them are very bright yellow. Other are the crystals are very orangey. Others are paler, and she has been able to characterize them all. And her crystal structures, especially in terms of the interactions that they form, are show how the properties of these dithiolanes, dimid and dimio structures can have, and their possibility as ligands, which is something that we're currently developing. Then also we have the work of and here, there is a video from Keisha on a lot of crystals, on crystal growing from this tube. So I hope that you can see this very bright formation of crystal that are starting to appear as she moves the camera. And this is, for me, it really shows how well she has been trained in observing crystal growth, and she is able to start this formation by just hitting a little bit the solution and just leaving it there for a couple of seconds. So this is, again, it's very simple technique, and it, for one of her compounds, it just works very beautifully. And unfortunately, I didn't have time to talk about the temperature factor on crystal growth, but that is a topic for another seminar. Then there is the work of student Javier Rivera, which has a student has worked in a lot of shift basis complexes, from palladium, platinum, now cobalt, and all of them has been characterized through X-ray diffraction. And he can see again the different torsion, actually the planarity of his system, and in some of them the torsion angles that there exists, and how this may be influencing the properties, the optical and spectroscopic properties of these complexes. So this is a very promising work. Let's see the next one. And this is the work of John Cruz, who is working with a lot of trifluorinated compounds and thiazines, talonitriles, in order to build different systems of phthalocyanins. And he is also very excited about the work of his crystal structures. Every time that he gets a crystal structure, this here in the right is an image that he sends me all the time from his cell phone, which again is just the recalculation of the structure, which doesn't necessarily mean that by having this into a program that predetermines gives you 100% accuracy, but it's a fast illustration on how the X-ray diffraction technique has developed. That right now it is quite easy to observe the arrangement of the atoms a priori. Okay, and next. This is again, these are some of the John's other crystal structures. And as a conclusion, I would say that I showed you just a few crystal structures from some of my students. And I think that they have been motivated by the fact that crystallography is a beautiful field, and that I love what I do, and training that they have received from my part have yielded them the excitement to pursue their work, their crystallography work, which is a very large component of their dissertation projects. And this is only because of the fact that I love doing crystallography, and I love teaching crystallography. And I think that because I love crystallography and I love teaching crystallography, in this way, my students are motivated by me, and I am motivated entirely by them in continuing doing this work. So I'm passionate about it, and I hope that you have received a little bit of excitement on crystallography through my talk. And this is the end. Thank you very much. Oh, sorry, there is one more slide. There is one more slide. I have to, because in this case, I have to thank my students that have done all the work to get all those crystals. Not only students from the Piñero group, which I thank them a lot. They are there at in the depth, but I also thank all the students from the chemistry graduate program that have given me so much love and have shared for me all this year. So thank you, Alejandro, and all the other students from the chemistry graduate program. I love you very much. The Molecular Science Research Center, thank you for hosting our facilities. The Material Characterization Center for support. And the Younger Chemists Committee, sorry about that, also, and the NSF grant that fund us. And then please, the last slide. This is the invitation to CERMAX, and I would like to see everybody here there. So with that, I am finished with my presentation. Thank you very much for the invitation. Thank you so much.
Thank you, Dr. Piñero, for